Okay, welcome everyone to my continuation. What is Matroid theory, or algebraic graph theory as I call it. And today we're actually not going to talk about matroids at all. Okay, yeah, fair enough. We're talking about matroid theory without talking about matroids. But we stay here, it will be worth it because we're talking about something that will apply. I have a little one here for matroids kind of in the second video on this, but just as a starter, I just want to talk about the greedy algorithm itself, because it's absolutely fantastic. It's absolutely great. It's this these very rare moments in life where you do something silly and it's actually the best thing you can do. It's just very, very strange. I really love it. And spoiler, what we will see is now really in general, but eventually I will tell you that matroids are essentially a perfect approximation to the greedy algorithm, in the sense that they are the only things where the greedy algorithm works. That's not quite true, but it's actually not that far away from the truth if you want. But anyway, today we just enjoy the greedy algorithm itself. And let me just make this a little bit bigger. Okay, so do not be greedy is, well, maybe a good slogan. So essentially, I think about the following problem. I want to find the maximum, and it's clearly here. And I don't want this maximum because this one is clearly much, much larger than the other one, right? I don't want to find the small one down here. But let's say I start here at my point A, and I'm very greedy. So I'm not taking anything global into account. I'm just taking something local into account. And locally, here the slope is kind of really, really small, and here the slope is much faster. So locally, kind of greedy. It makes sense to just walk in this direction, and eventually I will find my little spot here, which is not the optimal one. So being greedy, we really shouldn't expect any greedy strategy to work. And greedy strategy in this video just really means do locally the most optimal thing and don't care about global options. Okay, like collecting coins on the street will not get you rich, but collecting coins is kind of locally the best option you have. Anyway, so greedy is not supposed to work, right? Completely ignoring the global setting. It's just, I mean, how on earth is that supposed to work, right? So in this above example, finding the maximum will clearly fail. And we can make it arbitrary bad, right? I could make bigger and bigger little maxima out here, and we'll never ever find them running a greedy strategy. So essentially what I'm saying is we should not expect this to work, right? So it's just not happening. It's really not happening. So my video is over. This is not happening. Being greedy, so doing locally the correct thing and ignoring the global situation is usually not going to work. So really don't be greedy. Video is over. I hope you enjoyed this video, and I hope to see you next time. Okay, maybe not. So the point is that sometimes the greedy strategy is actually optimal. And this is kind of remarkable if you think about it. I give you an example right now. But if you just think about it, it's really remarkable. If you just ignoring the global situation, how can that ever work? I mean, this is just ridiculous. But it works quite often, actually. So let's say here's a greedy strategy. So you want to give kind of the minimum number of coins for change. Let's say you need to do 36. You need to give 36 coins. That's my currency here, coins of change. And let's say you have 20, 10, 5, 1, the usual ones. And the way to do it is just to do the greedy strategy. Always place the biggest one first. So 20 goes into 36, so take 20 first. Good. The remaining one is 16. So 20 doesn't go into 16, but 10 goes. So we take 10 next. 5 goes into the next one, 1 goes into the next one, and this is the optimal amount of change. And I really did an absolutely greedy strategy here. I always took the biggest one that fits. Right? I did locally the correct thing, and by magic, I get globally the correct thing. And this algorithm is just remarkably simple. And that's the whole point about greedy strategies. If they work, they're just simple as fuck, right? They're just really, really easy. In this case, we don't really need to worry about anything. Just always take the biggest that works. Always take the biggest that works, and you will get the optimal solution. Ridiculous, absolutely remarkable. It's an example of a greedy strategy. So maybe what I said on the previous slide, don't be greedy. Maybe it's a bit fishy, and maybe actually being greedy is not so bad. In this example, it is. So in this, well, giving coins for change example, being greedy is actually a really, really good idea. There you go. Here's another one, maybe more related to our matroids. Let's say we want to find let's say we want to find a spanning forest, spanning tree, whatever you want. So in a connected setting, it's just a spanning tree. But anyway, and it works as follows. You always just do locally the thing. You just pick an edge. So here we pick an edge. Fine. We just pick an edge. We pick another edge. We pick any other edge. We pick another edge. And we just do it having one local condition, namely we don't want to create a cycle. And just picking edge actually works. You never create any problem, and eventually you get a spanning forest or a spanning tree. And you can do it even better. You can do this weighted. So in the following sense, I will do this now. It's a bit nicer to see on this example. So as you can see, there's little numbers on the edges, and I don't want to find any old forest, any old spanning tree, but the one with the minimal weights on the edges. So if you just sum them up, so this has 1, this has 4, this has 8, and so on. And I'm looking for the minimal spanning forest in this case. And it really is just the completely absurd strategy that finds it, the greedy strategy. I take the edge with the smallest label first. There's only one, I take it. I take the edge with the next smallest label, I take the edge with the next smallest label, and I continue. I take the edge with the next smallest label, take the edge with the next smallest label, and so on. You really just order the edges and take them one by one. And the only situation where you don't take an edge is the locally obvious one, namely if you create a cycle. That's not what you don't want for a tree. And that strategy works. It produces a minimal tree. So the strategy, pick the smallest edge, is just working here. This is just extremely remarkable. I mean, come on, this is absolutely not trivial that is supposed to work. I mean, there could be some subtleties in picking edges, or you might run into trouble that eventually you can't pick the edges anymore you want because you would create cycles or something. But no, you don't. This ridiculously simple strategy works. And it's just, I don't know, it's just remarkably great. It's just absolutely fantastic. Yeah, so there's like zillions of greedy strategies. My favorite one is the pizza division, or the Egyptian fraction one. So Egyptian fractions is kind of this old, I think they found it in Egyptian tombs. So Egyptians considered the question, well, there's something like we have 5/8, and we want to write it in terms of 1 over something plus 1 over something plus 1 over something. And this is really, if you think about it, dividing, let's say, 5 gold bars, like here, into 8 under 8 people. So how do you do that? Well, everyone gets a half of a bar and everyone gets an 1/8 of a bar. It's exactly the point. So you half the first one first, so everyone gets half of a bar. So here you have 8 of them, and everyone, oops, this was really bad, and everyone gets an 1/8 of a remaining bar. And that's exactly this Egyptian fraction. It's the idea of how to divide pizzas or cakes among people, if you want. And this one has a greedy strategy, so you can compute 1/2 and 1/8 from a greedy strategy. I'm not going to explain that now. Finding shortest paths is a greedy strategy. It's just ridiculous. It's just ridiculous how many problems have a greedy strategy. Again, for the Egyptian fractions, you never run into trouble if you do the greedy strategy. It's really, really amazing. And the point will be, right now that's a little bit vague, but the point will be that matroids always produce situations where a greedy strategy applies. And that's just really remarkable. And even a bit better, so the converse is not quite true, but it's almost true. It's almost true that whenever a greedy strategy applies, there's a matroid around. So I said it's not quite true, but it's not that far away from the truth. So essentially, matroids are the settings for greedy strategies, which is just absolutely fantastic. It's just absolutely. As I said, they should not apply. And greedy strategies are even better. So okay, if they apply, if they work, they give the optimal solution, then you have just a ridiculously simple algorithm. Just do locally the best and just do it and done. But part of greedy is what I call almost greedy. So very often it actually happens that greedy doesn't give the optimal solution, but gives a really good approximation on the optimal solution, which is still very good because sometimes a problem is just really, really hard. And finding an optimal algorithm is just very demanding and it has a long runtime or whatever. And very often still a greedy strategy doesn't give you the best answer, but it gives you a really good answer. And maybe that's actually enough in practice. So here's an example of greedy coloring. It really works as follows. You just have a graph, this one. So the graph is just what you see in the background. I have two different colorings here. And coloring is NP complete. So it's really hard and complicated. But the greedy coloring is the following, and it works very often in a very good way. You just number the vertices in any way you want, 1, 2, 3, 4, 5, 6, 7, 8, and give every vertex the smallest available color. So let's say red corresponds to 1 and blue corresponds to 2, then the smallest available color for 1 is red. The smallest available color for 2 is still red, because 1 is not connected to 2. The smallest available color for 3 is still red, because 3 is not connected to any of them. For 4, it's still red. 5 is now connected to a red one, so we give it the next color, blue. Blue, 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 and you, by magic, end up with the optimal coloring. And it was really, really simple. You just did something local. What is the smallest available color? Note that it's not quite optimal, because if you choose things differently, and let's say green is 3, and what is it, yellow is 4, then you will, yellow is really difficult to read. You shouldn't use yellow. So let me make yellow maybe a little bit more readable. Orange. So my orange here is now yellow, whatever. And you get a different color. So it's not optimal, but very often gives you good results. And you can kind of make a really good estimate of what very often means in this case. Anyway, so the point of next video will essentially be that greedy and matroid is the same, which justifies for me the whole definition of a matroid, because greedy algorithms are really rare and you should really look for them, because they're exceptionally simple. Just unbelievably how simple they are. So should we be greedy or should we not be greedy? I leave the decision to you. Anyway, I hope you enjoyed this video, and I also hope to see you next time.